Hello physics students and welcome to Rotational Dynamics. In this video we are going to look at three main topics. The first one will be how Newton's second law applies to rotating objects. We're going to look at angular momentum, and then we'll look at rotational kinetic energy. First, let's look at Newton's second law for rotating objects. Here's our equation. When we talk about Newton's second law, we are looking at the idea that an object in motion tends to stay in motion and resists changes in that motion, and it works for rotating objects as well. And for rotating objects, Newton's second law is expressed as net torque. Remember, torque is a Greek letter tau, and that is equal to the moment of inertia, represented by the I, times the angular acceleration, alpha. Remember that a positive torque causes an object to rotate counterclockwise. Also, that means the angular acceleration of that object would be counterclockwise as well. Conversely, a negative torque produces a clockwise angular acceleration. So the sign on these is very important. Let's look at comparing Newton's second law for translational motion with Newton's second law for rotational motion. When we talk about translational motion, remember it's force equals mass times acceleration. And when we're looking at the rotational motion, it's our equation that we just learned. So let's do a sample problem using Newton's second law for rotational motion. A student tosses a dart using only the rotation of her forearm to accelerate the dart. The forearm rotates in a vertical plane about an axis at the elbow joint. The forearm and dart have a combined moment of inertia of 0.075 kilogram meter squared. That's a invisible multiplication dot right there. That's the moment of inertia about the axis, and the length of the forearm is 0.26 meters. If the dart has a tangential acceleration of 45 meters per second squared just before it's released, what's the net torque on the arm and the dart? Let's write down what we know. Here is what we know. We know the moment of inertia, we know the tangential acceleration, and we know the distance. That would be the length of the forearm. And we want to find tau, or the torque. We know that torque equals the moment of inertia times the angular acceleration, but whoa, wait a minute, we don't know the angular acceleration, we only know the tangential acceleration. So let's calculate that angular acceleration. Remember that tangential acceleration is equal to the radius times the angular acceleration. So we can plug values in here and solve for alpha. So I can solve for alpha as being 173 radians per second squared. I can now plug the appropriate values into my equation for the torque, and I'm just eliminating the units because I'm running out of room, but torque equals the moment of inertia times the alpha that I just found. And when I do the math, the torque is 13 Newton meters. Now let's take a look at momentum and how momentum is different when we are traveling in a circle. Remember that when we talk about translational momentum, momentum is represented with a lowercase p, and that equals mass times velocity, p equals mv. When we talk about angular momentum, we are going to look at this equation. L, capital L, is the letter that we use to represent angular momentum, and that equals the moment of inertia times the angular speed. So comparing the two, that's how they are different. So the law of conservation of angular momentum states that when the net external torque acting on a rotating object is 0, then the angular momentum of the object does not change. In other words, the initial angular momentum is going to be equal to the final angular momentum. And when we look at an example of an ice skater skating, the friction is negligible, so we can say that no torque is acting on the skater. And if we look at the skater here in this diagram, her initial angular momentum is being represented by L sub I, is going to be equal to her final angular momentum when she brings her arms and her feet close together. And how can this happen? You know that when her arms and legs are further away from her axis of rotation, that the moment of inertia is greater because the mass, on average, is further away from the axis of rotation. When she brings her arms closer together, the moment of inertia is smaller than in the initial moment of inertia because the mass, in general, is closer to the axis of rotation. Therefore, the angular speed final is going to end up being larger, and she will go faster in this situation than in this situation. Let's look at a problem regarding this. Let's say we have a 65 kilogram student spinning on a merry-go-round, and the merry-go-round has a mass of this and a radius of this, and this student walks from the edge of the merry-go-round, it's a really, really big merry-go-round, toward the center. If the angular speed of the merry-go-round is this initially, what's the angular speed when the student reaches this point away from the center? So I'm going to write down everything I know. I know the mass of the merry-go-round, and I'm going to write that with a capital M because that's going to have to do with the moment of inertia for that merry-go-round. I'm going to write a little m for the mass of the student. And my initial radius for the merry-go-round as well as for the student is 2.00 meters because the student is on the very edge, the outermost edge. And that's the radius of the merry-go-round as well. My final radius is when the student is 0.5 meters, and my initial angular speed is 0.2 radians per second, and I am wanting to find my final angular speed. I'm going to write a few more things down. I'm going to write down moment of inertia formulas here. The moment of inertia for the merry-go-round is 1/2 mr squared because the merry-go-round is a disk or cylinder about a symmetry axis. The moment of inertia for the student initial would be m with the lowercase m because we're talking about the mass of the student, and r squared is just simply going to be this number here squared. The moment of inertia for the student final is going to be the mass of the student times rf squared. I'd also like to point out a couple of things. The moment of inertia for the merry-go-round initial is going to be the same moment of inertia that it has in the end. And also, the angular speed for the merry-go-round initially is also going to be the angular speed for the student initially, as well as the angular speed for the merry-go-round final is going to be the same as the angular speed for the student final, because the student is on the merry-go-round kind of attached to it. So those would be the same. So I'm going to assume no torque acting on this situation, and therefore I can say that angular momentum is conserved. Initial angular momentum equals final angular momentum. I can expand that to say then the initial angular momentums added together would be the angular momentum of the initial angular momentum of the merry-go-round plus the initial angular momentum of the student is equal to the angular momentum of the merry-go-round final plus the angular momentum of the student final. I know that angular momentum equals moment of inertia times the angular speed. So the angular momentum of the merry-go-round initial is going to be the moment of inertia of the merry-go-round, which is the same initial and final, times the angular speed initial. The angular momentum of initial of the student is going to be equal to the moment of inertia of the student initial times the angular speed initial. And I just substituted these other values in for the angular momentum as well. I can just use the distributive property to rearrange these so that I'm not having to write the things so many times. I just pulled the angular speed out and multiplied in that way. I can substitute now my equations for moments of inertia into this, and I end up with this equation. At this point, I can directly substitute values in for these variables, and I can do that now. And that is what our equation looks like with the values all substituted into it. When I do the math, I get the answer to be 0.25 radians per second. So just as our translational kinetic energy was equal to 1/2 mv squared, we also have rotational kinetic energy. And rotational kinetic energy can be calculated using this equation, 1/2 I omega squared. So in this case, the kinetic energy is rotational, and the I is the moment of inertia, and our omega is the angular speed squared. So if gravity is the only force acting on objects, if we can assume that friction is negligible, then mechanical energy is conserved. And that means that our mechanical energy initial is equal to mechanical energy final. But remember that mechanical energy is the sum of all types of kinetic and potential energy. So we have to include rotational kinetic energy in our formula for mechanical energy. So our mechanical energy formula looks like this, including both translational kinetic energy and rotational kinetic energy, as well as gravitational potential energy. When we substitute values in, of course, the translational kinetic energy is just 1/2 mv squared, and the rotational kinetic energy is 1/2 I omega squared, it should be. Sorry about that, I forgot that term. And we can use this to solve problems. Let's try a sample problem. Let's say we have a ball that is solid with a mass of 4.10 kilograms and a radius of this, starts from rest at a height of 2 meters, rolls down a 30-degree slope. What is the translational speed of the ball when it leaves the incline? So I wrote down all of the things that I know. I know the height is 2 meters, the theta is 30 degrees, the mass of the ball is 4.10 kilograms, the radius of the ball is this. The initial velocity is 0 because it's starting from rest, and I want to find the final translational velocity of that ball. I'm going to apply the conservation of mechanical energy in this situation. Mechanical energy initial equals mechanical energy final. I also know the initial mechanical energy is all potential energy, and I know that the final mechanical energy will not have potential energy involved. It will just be the translational plus the rotational kinetic energy. These are my terms for, this is translational kinetic energy and rotational kinetic energy. I also know from previous sections that angular speed is equal to tangential velocity over r. So when I think about that, I know that my final angular speed is equal to my final velocity, my final tangential speed, divided by r, and I'll be able to substitute that in right there. Also, I know that the moment of inertia for a solid ball, which I found on my little moment of inertia table, is equal to 2/5 mr squared, and I'll be able to substitute that in right here. So when I substitute those terms in, I just plugged in 2/5 mr squared for that, and I plugged into here VF over R, and of course then needed to square it, and that's what this equation represents. Now I'm going to simplify this a little bit. I know that I can cancel these 2's out when I multiply those together. I also know that VF over R squared is the same as VF squared over R squared, so my R squared terms can cancel out, and I can rewrite this equation like this. And now I can actually do some combining. I have two terms that are the same, mvf squared and mvf squared. 1/2 plus 1/5 equals 7/10 mvf squared. And if I look at just these, this equal to this, I can cancel some terms out, like my mass. And I'm left with GH equals 7/10 times mvf squared. Now I can plug values in and solve for VF. And actually, I made a little mistake here. I wrote that M that shouldn't be there. That had been canceled out. When I plug values in for all of that, I can solve for my VF. Remember to take the square root before you solve, and my answer is 5.29 meters per second. So if you're looking for advanced proficiency, you can make up your own problems, or you can try and solve that extra problem number 3 on practice 8E on page 297 of your textbook. If you have other ideas, bring those in, and I look forward to seeing you in class.